You know that moment when someone can perfectly, like, recite a definition back to you, but then you ask them to actually use it or apply it, and it all just kind of falls apart? Or maybe you've seen an AI give this flawless answer, but a simple follow-up question just reveals this baffling lack of real understanding. Well, that exact kind of disconnect, that's what a really groundbreaking new paper is digging into. So today, we're doing a deep dive into Potemkin understanding in large language models. It's a fascinating study. It comes from a brilliant team, MIT, University of Chicago, and Harvard. And this research, it really cuts right to the heart of a super critical question. How do we really know if these powerful LLMs, like GPT-4o or Claude 3.5, genuinely understand the concepts they talk about, like beyond just acing some test we give them?
Exactly. And our mission today really is to unpack this whole idea of Potemkin understanding. We want to show you why this isn't just some, academic footnote. It fundamentally changes how we should be evaluating and trusting and maybe even building AI going forward. You'll actually discover some pretty surprising things about how these LLMs seem to perceive concepts. It might challenge what you thought about their intelligence.
Yeah, we're going to explore their really ingenious framework, walk through some specific, quite telling examples, and really dig into the implications, which are pretty profound for the future of AI development. Okay, let's get started then. So maybe let's kick things off by thinking about benchmarks first. Those standardized tests we're all familiar with. When we evaluate humans, right, like for an AP exam or a medical board test, these tests are designed, supposedly, to measure genuine, applied understanding. If you pass a game theory exam, well, we reasonably assume you actually get Nash equilibria, for instance.
Right. But what's truly fascinating here, and what the paper highlights, is how that interpretation has kind of shifted for machine learning. For older, more specialized models, maybe like a pathology classifier that looks at X-rays, success didn't mean it understood vision in some broad sense. It just meant it performed well on that specific data. But now, with LLMs, we've started making this much bigger leap, haven't we? Success on those same human-designed benchmarks. It's often being hailed as evidence of, broader conceptual understanding.
That is a huge leap, isn't it? If that old pathology model was just performing but not really understanding vision, why are we so quick now to say an LLM understands just because it aced a human test? Is there a risk we're sort of anthropomorphizing them too much? Or maybe missing something really crucial in how they're actually processing information?
And that leads us right into the core idea of the paper.
Mm-hmm.
What if that success on a benchmark? What if it's just an illusion of understanding? This is precisely what they've termed Potemkin understanding.
Right, and it's such a perfect name they landed on for this, isn't it? Drawing from that piece of history, it's surprisingly relevant to AI. You picture a Potemkin village, this, elaborate fake front built to look impressive, but there's nothing really substantial behind it. Well, that's exactly what Potemkin understanding describes in an LLM. It looks like it gets a concept, answers questions perfectly, but its underlying interpretation, fundamentally different from how any human would see it. It's like an intellectual mirage.
Yeah, and the core insight here is that when humans misunderstand something, those misunderstandings, they tend to be structured, they're kind of predictable. A well-designed exam for people, like a clever riddle, it actually exploits these common human ways of getting things wrong to really test understanding. But, and this is the key, if an LLM's misunderstandings are completely different, if they diverge from those human patterns, well, then it can still score really high on our benchmarks without genuinely grasping the concept at all.
Think about this example they give in the paper. It's really powerful. GPT-4o, right? It could correctly explain an ABAB rhyming scheme, perfectly. First and third lines rhyme, second and fourth rhyme. Got it. But then, okay, try and generate a poem using it, and it just completely failed. Produced lines with, no rhyme whatsoever. And here's the kicker. When they then asked it to identify rhymes in its own output, the LLM seemed to recognize its words didn't rhyme.
Exactly. That specific combination. The perfect definition followed by a totally contradictory application. And then awareness of the contradiction. It's irreconcilable with how a human would fail. Like you said, a chef describing a souffle perfectly, then serving raw eggs.
Yeah, that's it. That right there is a perfect illustration of a Potemkin.
So to try and formalize this kind of unsettling idea, the researchers defined something they call a keystone set. Now, for humans, a keystone set is like a minimal group of questions or examples where if you get all of them right, if you interpret them all correctly, it logically implies you actually understand the full concept. So, for instance, being able to correctly define the 575 syllable structure and maybe identify a simple example, that might be a keystone for understanding haikus and people.
Okay, so a Potemkin then happens when an LLM aces all the questions in that keystone set. It gives the perfect definition, maybe identifies an example. But fundamentally, deep down, it does not have the correct interpretation of the concept itself. And this is a really crucial point, isn't it? Because it means those human-designed benchmarks we rely on, the ones that assume a human-like understanding, they're actually invalid tests for LLMs if these Potemkins are floating around. It suggests a pretty fundamental flaw in how we're currently evaluating them.
Okay, so we've got a handle on what Potemkin understanding is and, yeah, why it's potentially such a big problem. But the real genius in this paper, I think, is how they actually went about testing it. How did they manage to, pull back the curtain on this illusion?
Well, they came up with two main procedures, two ways of measuring this. The first involved actually building a specific tailored benchmark, one designed explicitly to expose this gap, this difference between an LLM's ability to explain a concept and its ability to, well, apply it. And they covered a lot of ground with it, right? It wasn't just narrow. They built this data set covering, 32 different concepts across 3 really diverse areas. Things like literary techniques, analogies, sonnets, then game theory, Pareto optimality, stuff like that. And even psychological biases, sunk cost fallacy, the IKEA effect.
That's right, a really broad mix. They weren't just testing, say, coding ability or something simple. These are complex, nuanced human concepts.
So what did they actually ask the models to do with these concepts?
Okay, so for each concept, they tested models on 4 different kinds of tasks, really trying to hit it from different angles. First, just definition. Can it define the concept correctly? Straightforward enough. Second, classification. Here's an example. Is it a valid instance of the concept or not? Is this a slant rhyme? Does this Reddit post show the sunk cost fallacy? Third, constrained generation. Can it actually produce new examples, but with specific rules? Write a haiku about friendship that has to use the word shield. And finally, editing. Can it take an existing example and tweak it, either to make it fit the concept or maybe to deliberately make it not fit?
Okay, wow. That's thorough. And the results they got, you said they were striking.
Oh, absolutely striking. So get this. LLMs define the concepts correctly an amazing 94.2% of the time. They could basically parrot back the definitions almost perfectly.
Okay, that sounds pretty good initially.
Right. But here's where the illusion just shatters. Conditioned on giving that correct definition, their performance absolutely plummeted when they were asked to actually use those concepts. This led to what they call the Potemkin rate, which is basically how often did the LLM get something wrong despite having just nailed the definition.
And that rate was?
It was high. Shockingly high, really.
Yeah.
Across all the models they tested and all the different task types. For classification tasks, the Potemkin rate was 0.55. So more than half the time, even after defining it right, they couldn't classify correctly. For generation, it was 0.40. For editing, also 0.40.
Wow. So 40 to 55% of the time they could explain it, but couldn't actually do anything meaningful with it.
Precisely. They can often perfectly articulate a concept, lay it out flawlessly, but when it comes to applying it, building with it, using it consistently, it's like the understanding just evaporates. And the paper gives these qualitative examples, too, that are just baffling. Failures that no human who actually understood the concept would ever make. Like defining the triangle inequality theorem perfectly, A plus BC.
Yeah.
And then suggesting 4 could be the third side of a triangle with sides 7 and 2. 7 plus 2 is 9. 4 is less than 7 minus 2 even. It's just fundamentally wrong.
Right, completely impossible.
Or defining what an uncle-nephew relationship is perfectly clearly. And then failing to identify a super obvious example of one. These aren't just small mistakes or edge cases. They point to something deeper, some kind of profound internal incoherence.
Okay, that first benchmark already sounds pretty damning. But you said there was a second procedure, one that went even deeper.
Yes, and this one is maybe even more revealing. They developed an automated procedure to evaluate for something they call incoherence, which is essentially asking, is the LLM's internal grasp of a concept consistent? Or does it hold, conflicting ideas about the same thing simultaneously?
Hold on, how do you even test an AI's internal consistency? That sounds incredibly difficult. What was their method for that? Sounds brilliant.
It really is quite clever. They basically made the LLM grade itself. So first step, they'd prompt a model, hey, generate an example of concept X, let's say a slant rhyme.
Okay.
Then, in a completely separate query, totally fresh context, they'd feed the model's own generated output back to it. And they'd ask it, okay, classify this. Is this thing you just made actually an example of concept X.
Whoa, so it generates something and then later has to judge its own work without knowing its own work. That's fascinating.
Exactly. And incoherence was then measured by how often the model's initial generation didn't match its later classification. Like, it generates something it thinks is a slant rhyme, but then later says, nope, that's not a slant rhyme.
Huh. It disagrees with itself.
Precisely. And the results. They found incoherence across all the models, all the concepts, all the domains they tested. The scores varied, from 0.02 up to 0.64 in some cases, which really indicates that their conceptual problems aren't just about misconceiving a concept in one specific way. It's about inconsistently applying whatever notion they do have, even moment to moment potentially.
Okay, so they took that self-grading insight and used it more broadly.
Yes, they leveraged that to develop a more general procedure, one that gives a lower bound on the overall Potemkin rate. It's a bit complex, but here's the gist. If an LLM answers some initial benchmark question correctly, great, step 1. Then they prompt it. Okay, now generate some other related questions about this same concept.
So the LLM makes up new questions.
Yes. Then the LLM answers those new questions it just generated. And finally, the crucial step. The LLM then grades its own answers to those questions it just created.
Okay, my head's spinning slightly, but I think I follow.
The point is, if the LLM's internal judge disagrees with its own answer that it just gave to its own question, that's flagged as a Potemkin. It's basically catching the AI contradicting itself in this more elaborate setup.
So it's like setting a trap for its own inconsistency, and this only gives a lower bound because it might be inconsistent in ways this method doesn't catch.
Exactly. It's a conservative measure. But even so, the overall Potemkin rate they found using this method was still alarmingly high. It came out at 0.62.
Wow, over 60%.
Yeah. And these findings really just hammer home the results from the first tailored benchmark. It powerfully reinforces this idea that Potemkins aren't some rare glitch. They seem to be, ubiquitous, pervasive across these models.
Okay, this is clearly a huge finding for AI researchers. Let's bring it back. What does this all mean for us, the people interacting with LLMs every day? And what about for the future of AI development? Because those numbers, 0.55, 0.40, 0.62, they are pretty jarring. I mean, playing devil's advocate for a second, couldn't someone argue that for a lot of everyday uses, if an LLM can define something okay and sometimes applies it right, isn't that maybe good enough for now? What's the actual danger here?
Yeah, that's a really crucial question to ask. And I think if we connect this to the bigger picture, what it implies is potentially quite profound. It suggests LLMs might not just understand concepts less effectively than humans, but maybe in fundamentally different ways altogether. And this is a critical distinction. The paper puts it really well. Potemkins reveal modes of conceptual understanding that humans, by construction, cannot exhibit.
Meaning, their way of not getting it is alien to us.
Kind of, yeah. It's not a human-like flaw, like just missing a detail. It's something else.
Yeah.
And the danger, I think, lies in building ever more complex systems, maybe even critical systems, on top of this apparent understanding that's actually revealed to be quite fragile, inconsistent, potentially unreliable when stressed or faced with novel situations.
The paper draws this really powerful analogy, which I think helps make it click. They say, Potemkins are to conceptual knowledge what hallucinations are to factual knowledge. And we're all getting pretty familiar with AI hallucinations now, right? Where a model just makes stuff up, fabricates false facts. But Potemkins, when an AI fabricates false conceptual coherence, it seems like it understands the relationships between ideas, but internally it's a jumble of contradictions.
Exactly. And that immediately raises a really important, maybe sobering question. Which of those two problems is actually harder to fix? Hallucinations, right, while super annoying and sometimes dangerous, can often be exposed. You can use external fact-checking databases, retrieval augmentation, try to ground the model in real data.
Right. There are strategies emerging.
But Potemkins, these subtle internal inconsistencies in apparent understanding, that feels like a much, much deeper challenge to unravel and genuinely address. But the good news is this research doesn't just point out the problem. It actually offers some critical, actionable tools to start identifying and maybe beginning to address these discrepancies. It gives us a way to look under the hood.
Wow. What a deep dive that was. So we've really uncovered that while these LLMs can, define concepts with truly impressive accuracy, their ability to actually apply those concepts, to reason with them consistently, while it often falls strikingly short. This whole idea of Potemkin understanding feels like a crucial, maybe even unsettling insight. It's a stark reminder that just looking good on a test doesn't always equal true comprehension. And maybe, just maybe, LLMs understand things in ways that are fundamentally alien to how human cognition works.
Absolutely. And the sheer ubiquity of these Potemkins, showing up across different models, different tasks, different domains, it really demands a profound re-examination of how we evaluate AI.
Yeah.
And maybe more importantly, how we decide to trust AI.
Yeah.
It strongly suggests that developing truly robust, reliable, consistent conceptual understanding in LLMs, well, that's a far more complex and foundational challenge than just chasing higher scores of the benchmarks we currently use.
So, for you, our listener, maybe consider this provocative thought as we wrap up. If an AI can perfectly define a concept, yet completely fail to apply it and even contradict its own reasoning about it, what does that imply about the very nature of the intelligence we think we're building? And maybe more personally, what other hidden Potemkin villages might still exist, quietly shaping your interactions with the AI systems you rely on, or maybe will rely on, every single day? We really hope this deep dive leaves you with plenty to think about.